Let's start by discussing signals and systems. These concepts are the absolute core of what we'll do in this class, so we need to understand very well exactly what a signal is and what we mean by a system. When we say a signal, we don't necessarily mean like a television signal or a radio signal or a cell phone signal. We're dealing with the concept of signal, a theoretical concept, and in our case, it stands for any ordered set of information. The order is established by an independent variable, and for us, this will usually be time. But it could also be, perhaps, a spatial variable, say distance. So here's our first example of a signal. This is the acceleration measured during an earthquake, and so you can see the acceleration plotted versus time. So the independent variable here that's ordering the information is time. Here is a second example where time is the independent variable. Plotted here are stock market averages versus the year. So signals can be quantities other than those typically found in engineering. Indeed, the concept of signals is used broadly in many different fields. Here is the DNA double helix, and this is a signal too. We have information in terms of the base pairs that is arranged. Here, the independent variable that's arranging these base pairs is a spatial variable, the distance along the DNA double helix. Now let's introduce the concept of a system. A system is any device or process that generates one signal from another signal. This is a very general concept. You could view an airplane as a system. You could view the human brain as a system. You can view a computer program as a system. Anything that takes one signal and produces another signal is a system. So a system takes one signal and produces another signal. We'll denote that here in this diagram by showing a signal going into a system and another signal coming out of a system. The system going into the system, the one that causes things to change, is referred to as the input signal. The signal coming out of the system, that is, what we observe, is referred to as the output signal. Systems may have many input and many output signals. In this class, we'll largely be studying systems with only one input and one output. The key thing to remember here is the input signal is the signal that causes things to change, and the output signal is just what we happen to observe. To make this more clear, let's look at a few examples. So here's a robot, and this is our system. The input is the motor voltage signal, and the output is the robot motion. For another example, here's another robot. The input here could be the voltage to the motor, the force acting upon the wheels, or the torque exerted by the motor. And the output could be the robot's position, its velocity, or its acceleration. From your previous mathematical background, you should have a good idea of what signals are. Signals are simply functions of time: pressure, temperature, force, acceleration, as a function of time. It should be mentioned that the signal is the whole function of time, not just the value of a particular variable at a particular time. It's the entire curve. But what about systems? Are systems functions? This is a question I'm often asked, and the answer is no. Systems are not functions. Let me explain why. Functions produce a scalar dependent variable when provided with a scalar independent variable. For example, y equals f of x. We put in the scalar x, and out comes the scalar y. We represent that with the graph, showing the relationship between the input x of the function and the output y. So functions relate scalars. While functions relate scalars, this is not usually true for systems. Systems do not relate scalar values. So what do systems relate? We already know what systems relate. They relate an input signal to an output signal. Now recall what signals are. Signals are functions of time. So, systems produce a dependent function when provided an independent function. Systems relate functions of time. They relate signals. So here's the way you should think about it. We have an input signal, x of t. This is the entire graph of x for all time. And it is the input to the system. It is the independent function. And in response, the system produces a dependent function. This is the output, y of t. It is a function of time. An input function produces an output function through the system. There is one exception to the rule I just gave you. There is one case where systems are actually functions, and this is the case of memoryless systems, which we'll study later. In this case, the output is produced from the input at exactly the same time. So in this case, the system can be considered a function. But this is the exception to the rule. I don't want you to worry about this particular point right now. It's a rather minor technical point, and it will become clearer as we move through the course. In the next 2 minutes, I'll overview what we're going to discuss in this course. We'll begin by talking about simple signal operations, things like how do you add signals and how do you multiply them. Then we'll move on to look at systems that act upon signals, and we'll look at linear systems which behave very nicely, and also at a class of systems which don't behave so nicely, the nonlinear systems. After we look at these systems and also causality and some other topics, we'll restrict our focus to linear systems, and we'll look at how they respond, both to inputs and also to initial conditions. Then we'll turn our attention to the behavior of systems in response to both inputs and initial conditions in terms of their stability or lack of stability. After that, we'll then reintroduce the Laplace transform, which you've encountered before. Hopefully this time, you'll fully understand the Laplace transform, what it means, and how we can use it to study systems. Then, after learning some Laplace transform properties, we'll start looking at mechanical systems in particular. We'll examine all sorts of mechanical systems, including this pinion system we see here. Our systems will have both torque inputs and also force inputs, and we'll look at displacement and velocity outputs. After examining mechanical systems, we'll then look at frequency response and time response, and these are very important topics in our discussion. And then finally, we'll look at some example problems where we can see how the tools we've learned in this class translate to the real world. That concludes our course overview. I hope you enjoy the class.